All right, let's take a look at the reactivity of some of our carboxylic acid derivatives. So again, we're going to just basically be doing this acyl substitution reaction where we have a nucleophile attack this electrophilic carbon, and it's electrophilic because it's doubly bound to an oxygen, and of course our other Y molecule, which is some other electronegative element. We have this very important tetrahedral intermediate, and then a lone pair from the oxygen kicks back down. In this case, kicks off this Y group to complete our substitution reaction, right? We've substituted the Y for some kind of nucleophile. This first step where the nucleophile attacks our electrophile is generally the rate determining step, although the other step is indeed important as well. So when we think about this reactivity, we can kind of think of this as some kind of like pseudo like SN2 type of reaction. And so generally when we have less substituted carbonyls, they're more reactive. And that, of course, has to do with sterics, right? If you have a bunch of bulky stuff, it's just going to be harder for that nucleophile to get on there, right? So if you have over here like R1, R2, and R3, that's not going to be as reactive as just having a methyl group there. And then, of course, what your Y group is also very important in terms of the reactivity. So we'll go from left to right, where right's going to be more reactive. And our most reactive group is going to be our acid halide. So that's why they're really cool. Overall, the chlorine is pretty electronegative, and it's a very good leaving group. So that's kind of what makes it more reactive. After that, we have acid anhydrides. Then after that, we have carboxylic acids and esters. And then finally, we have amides as the least reactive, right? So as we go towards the right of this chart, we get more reactive. We won't take a look at too much into the nuances. If you'd like to explore more of the nuances, stop by my office hours, or you can read the book. There's multiple factors that go into it, so I don't want to go too deep into it because it can become confusing. So we're going to ask, why. We're just going to say inductive / resonance effects. Just some trends to point out, right? Notice that chlorine, when we learned about our electrophilic aromatic reactions, that was a deactivating group. This was also a deactivating group, where these over here were activating groups. So that plays a role in it, but it's not the complete story. We're just not going to get into it because I think it's just going to be more confusing than it is helpful. So in general, it's easy to go from something that's less, or from something that's more reactive to less reactive. Which makes sense, right? Ball rolls downhill because it goes from being more reactive to less reactive, right? Lower potential energy, that kind of thing. And again, that's why acid chlorides are so useful, because we can turn them into pretty much any one of our derivatives very easy, right? So this reaction up here would be easy to do, but doing the reverse would be more difficult, right? So for example, taking amide, the least reactive, and turning it into an acid chloride would be more difficult because it's the more reactive, right? So it's going to be hard. That doesn't mean that it can't happen. We'll learn plenty of reactions where we go from something that's less reactive to something that's more reactive. It's just more difficult to do. We need to use stronger reactants and usually harsher conditions. But overall, we'll learn a whole bunch of these acyl substitution reactions. They all get their name basically based on what we're going to change this Y group into. So for example, if you change this Y group into water, or if you add water to change this Y group into an OH for a carboxylic acid, that's called hydrolysis. We're breaking that bond using water to form a carboxylic acid. We could do a similar thing with an alcohol instead of a water molecule to form an ester in this case. That's called alcoholysis. Right, pretty self-explanatory why they give them these names. You can use amines, doesn't have to be NH3, you can use like NR2, you can add other R groups there. That's called aminolysis. And then, of course, we could add some kind of reducing agent to do some kind of reduction, right? We could reduce this down to an aldehyde or further reduce it down to an alcohol, right? And then obviously that's reduction. So we'll learn a lot of different reactions if you just like count them based on the number-based thing. But overall, most of them are pretty much going to be the same reaction over and over again.